vector transformation from cylindrical to Cartesian system. First, let's take a look at a point in cylindrical system. A point P has three components, ρ, phi, and z. Rho is the distance between the point and the z-axis. Phi is the angle that the line from the origin to the point on the xy plane makes with the positive x-axis, and z is the same as in Cartesian system. Now to transform a point from cylindrical to Cartesian, x equal to rho cosine phi, y equal to rho sine phi, and z in cylindrical equal to z in Cartesian. And to transform a point back into cylindrical system, rho equal to the square root of x squared plus y squared, phi equal to the inverse tan of y divided by x, and z is still equal to z. Now for a vector in cylindrical system, a vector v placed at point P, the vector also have three components, rho, phi, z. Now to make it easier, we're going to call the component of the vector as v rho, v phi, v z, and the component of the point as b rho, b phi, b z. For a point, phi was the angle between the point and the positive x-axis, but for a vector, phi is the amount of units in a circular motion around the z-axis. For example, if we have a force of 5 Newton, this force is going to be represented along a circle centered on the z-axis, but because we cannot have a circular vector, we use the tangent of the circle. Notice that the angle between rho and phi is always 90 degrees, which make the axes in cylindrical system perpendicular to each other, just like in Cartesian system. If we rotate the vector around the z-axis, as the angle of the point p phi changes, the direction of rho and phi also changes, which means if we have the same vector, let's say vector 2a rho, placed at different points in space, this vector is going to have different directions depending on the position of the vector. To transform a vector from cylindrical to Cartesian, we notice that z-axis is the same for both systems, so we only need to worry about rho and phi. So if we switch to the top view, we notice that the angle of a rho is equal to b phi, and the angle of a phi is equal to b phi plus 90. Now all we have to do is to take the component of rho and phi along x and y by taking the cosine and sine of their angles. So along the x-axis we have a rho cosine b phi plus a phi cosine b phi plus 90. And along the y-axis we have a rho sine b phi plus a phi sine b phi plus 90. The last thing we have is that cosine b phi plus 90 is equal to minus sine b phi, and sine b phi plus 90 is equal to cosine b phi. So we can replace them into the equations. Now, something important to note here, that ax and ay is not the unit vectors of the Cartesian system, but they are the unit vectors of the cylindrical system represented in the Cartesian system. And this is why the unit vectors of x and y are not in the length of 1. Now let's take a look at the unit vectors in different positions. Let's go to b phi equal 0. Here, a rho is equal to ax, and a phi is equal to ay, which make the cylindrical system identical to the Cartesian system when b phi is equal to 0. If we move to b phi equal 45 degrees, here a rho and a phi cancel each other on the x-axis, and they have the most amount in the y-axis. at 90 degrees, a rho is equal to ay, and a phi is equal to minus ax. Last thing to do is to rewrite the transformation equations in a matrix form and take the inverse of the matrix to be able to convert back from Cartesian into cylindrical.